Okay, and welcome to this video on resonance structures. Resonance structures occur when we are able to draw several correct Lewis structures. And before I dive into an example, let's get some key points down. When we move electron pairs, we will also be moving charges. So say we have atom A and we have a lone pair. We can move this lone pair and place them somewhere in the molecule, or we could have a bond on atom A and we could break that bond and place those electrons, those pair of electrons somewhere else. So the next key point is only electrons move. We are not moving atoms. The real molecule is the resonance hybrid, which is a combination of all the resonance forms. However, some forms contribute more than others, and I'll go over those rules at the end of our example. So let's move on to our example. Okay, this is what our resonance structure should look like. We have double arrows between each of them, indicating that we can go from here to here, here to here, here to here. Doesn't matter which way we go. And we have closed brackets. And do we have our charge? We do have our charge. It's kind of hard to see right there because this has a negative charge, so it's negative. Negative plus a negative is two negatives, plus a positive is one negative, and we only have a negative right there. Okay. Now I will show you how to go from here to here. We could go here to here, doesn't matter. Right now we're going to go from here to here. Okay, these lone electrons we are going to move, or it doesn't matter which ones we move, we'll be making a bond. If we break a bond, we will gain a lone pair. So I'll show you what that means. Okay, first off, we have a double bond on this oxygen, but we have a double bond on this oxygen that's connected to a hydrogen. How they went from here to here, they took this pair of electrons and placed them right here to make a double bond. So, electrons are negatively charged, and currently this oxygen is neutral, as 0. So, when we lose a negative charge, we are gaining a positive charge. That's why there is a plus right there. Okay, so let's draw this. We have right now we have a double bond, and we got rid of these. We do not have those. So we have 1, 2, 3, 4, 5 bonds on the carbon atom, which is not okay. So what we'll do here is we'll break the double bond and take those pair of electrons and make them a lone pair. When I say bonds broken equals lone pair, that is what I mean. So we broke this bond, and now we have a pair of electrons up here. It was previously neutral. See, there's no charge on it. So when we add a negative electrons, because they're negatively charged, we will gain a negative. So that's why they have a negative right there. And that is how they went from here to here. This oxygen doesn't change because we didn't do anything with it. We didn't move electrons at all. So let's move on to from here to here. All right, we have a double bond on this oxygen, but we have a double bond on this oxygen. So what they did here is they took these electrons, or these, it doesn't matter, just one pair, and they moved them to form a double bond. Now look, we have a negative charge originally. So when we're losing a negative charge, it wouldn't be a positive because we're already at a negative, it'd be 0. Because 1 plus a negative is 0. So like 1 plus negative 1, I meant to say, would be 0. That's why there's no charge right there. So let's do that. Let's have a double bond right there. Let's get rid of this and this because it's now neutral. Okay, we have 1, 2, 3, 4, 5 bonds in the carbon. We can't have that, so we must break the double bond. So let's break the double bond, take a pair of electrons, and place them right here. Look, we have a positive charge. So what does that mean? We're adding a negative to our positive, so that will be neutral. So we would get rid of this and have 2 electrons right there. Keep in mind this bond's broken, so this bond's not here anymore. So we'd have 1, 2, 3, 4. And that is how they got from here to here. Now, we could go from here to here. It doesn't matter. It just takes more time. So I'll just show you anyways. So we have a double bond on this oxygen, and we have a double bond on this oxygen. So what they did here is they took these electrons, placed them right here, made a double bond. We lost our negative charge, but we already have a negative charge, so that goes to neutral. So We now have a double bond here because we moved those electrons. Now we have 1, 2, 3, 4, 5. We can't have that. So what we must do is move these electrons over here, and we'll get that negative charge like we have over here because we broke that bond. So then we'd have 1, 2. We would not have that anymore. 3, 4. And that is how they go from different resonances. It's pretty easy, pretty quick. You could check the formal charges or the charges by doing the formal charge formula, which is, I'll just write right here, formal charge. This is the one I use. I think it's easier. We take the valence electrons minus, let me write that a little bit better, valence electrons, subtract it by number of lone electrons, so of lone electrons, plus the number of bonds. Okay, so I'll just do all in parentheses, remember that. So I'll do this oxygen right here. So oxygen is found where? I believe in group 16, so it has 6 valence electrons. We'd subtract. How many lone pairs do we have? We have 2 lone pairs, but a total of 1, 2, 3, 4 electrons. And we would add the number of bonds. Double bond counts as 2, so plus 2. A triple bond counts as 3. A single bond counts as 1. So 6 minus 4 plus 2, which is 6. 6 minus 6 is 0. And that's why this is a neutral charge. There's no charge on this atom. So that is that for that example. But we must ask which one is a major resonance contributor, because it says some forms contribute more than others. So which one's the major? Well, let me clean this up. Oops, let's get this. Okay. Which is the best? Let me move this over. Octet is always the best. If you have an octet around every atom, that is your best major resonance contributor. If they all have octets, like in this case, we have an octet on 2, 4, 6, 8 on this oxygen. We have an octet on this one, 2, 4, 6, and we have a single bond here, so it's 8. A duet, which is what hydrogen can have. So all these have octets if you count them. Okay, then what? Minimum of charge separation. So we can automatically get rid of the middle one because it has charge separation here, a plus and a minus, and a plus and a minus here. So it's 2 instances of charge separation. So this one would be our minor. So who would win the tie between these two? Well, let's keep looking. Most electronegative atom has the negative, meaning oxygen is the most, if you look at the periodic table, the most electronegative atom. Say there's a nitrogen in here as well. If the negative was on the nitrogen, that would not be good because we want it on the most electronegative atom, which is oxygen. So it's on there. Now let's look over here. Oh, it's on there too. Is there any difference between them? No. They are both major resonance contributor. They are both of equal contribution. So these two influence the resonance hybrid as we see up here. Resonance hybrid equally. The minor does not influence it as much, but it still makes a small contribution to the resonance hybrid. None of these atoms alone represent the molecule. It is a combination of all three. So that does it for this video. I hope to help.